So a naive translation could, for instance, replace all instructions, let's say all problematic instructions, with an int3, right? int3 causes a trap, and that's good. This is only 1 byte, so it'll fit anywhere without overflowing the existing size of an instruction. The big problem is when to do this. At load time, we load a bunch of stuff into memory. So we have our disk, we load chunks into memory. So we're in our address space, and we put all this stuff in here, and we've got a bunch of stuff in here. And it's bits all the way up. The problem is, how do we know, for example, which of these are instructions and which are data? So we don't know that. We also don't know, because again, keep in mind that the x86 has variable length instructions, where instructions start. So even if we knew something were instructions, we don't know where in there the instructions necessarily start. And if you've done disassembly of code, you'll see that depending on the address you actually put in, you may get garbage at the beginning, may get what look like very weird opcodes, because they're actually the tail end of a full opcode. Right? If you've got an opcode that is 3 bytes, and you disassemble it starting here, then you're going to get the correct instruction. But if you start disassembling here, that's the suffix of a valid instruction, and we don't really know what it's going to be. And depending on how long this not real instruction is, right? If it thinks this is itself a 3-byte instruction, then all of a sudden your next instruction is wrong, and so on and so on. Sometimes it'll think maybe this is a 2-byte instruction, and all of a sudden you'll synchronize up. But in any case, we can't find the instructions. That's the problem. How do we know what are instructions and what are not instructions? The only way we really know is look and see where we start executing. So we do know the start address. We know when we loaded this that there was a particular point in here that we're going to start executing instructions. Let's say it's here at that address. So we know that's an instruction. And if we disassemble that instruction and look at it, we know how long it is. We'll know, assuming it's not a jump instruction, right, or a call instruction, that the next byte after however many bytes this instruction is itself another instruction, and so on. So we can determine which of the instructions by what actually attempts to be executed. Now we have to figure out what we're going to actually translate. So we're going to work translating dynamically. This is not unlike a JIT compiler, so JIT standing for just in time. Here we're doing just in time translation. So we translate, let's say, from the kernel entry point to the first jump. And then once we make that jump, we start translating wherever we jump to the next jump, and so on and so forth. So we're going to do this in blocks. Chunks, which we're going to call basic block. So a basic block is either 12 instructions or when we hit a control flow instruction. Whichever one is first. So what we're going to have then is a bunch of little blocks that we're going to be generating on the fly. And our goal is for most of these, we're going to just do a identical translation. So if our original is here, then we want to translate it identically. And that can be done as long as we don't have any instructions that are a problem. So some of the instructions that could be a problem certainly are accessing the CS register. But while we're at it, we can just go ahead and do any privileged instructions here. We can go ahead and look for a CLI or an STI and replace that with some other code. So if we have, for instance, some code in here that includes a CLI, then we can convert this to, so the beginning part of the basic block can stay the same, the ending part of the basic block can stay the same. So this is identical, identity transform, this is an identity transform. And the CLI, we can translate, instead of a trap, which would cause us the cost of having to actually have a hardware trap, we'll just go ahead and put new code in here. So code that emulates a CLI. And we can do that for all instructions if we want. Any privileged instructions, we can go ahead and decide, just put in some code that does the right thing. It may be a call out to a VMM routine that does something, or we may just be able to put some inline code in order to deal with it. So there are some issues about this. The first problem we have is, how do we deal with memory? That is, we have the guest OS and its memory, but then we also somehow need the VMM itself, right? Where is this binary translation code living? And what we're going to do is so this is our address space. We're going to actually break it down into the part that the guest kernel has access to, and then a high part that is only accessible by the VMM. We are not going to be using paging for this. So we are not going to do protection in paging depending on the CPL, where this would only be accessible by user and this would be inaccessible by user. Okay, because that can be expensive because we're going to be dealing with page faults and we don't have to deal with page faults. So instead, we use segmentation. So what we do is we have all of the segment registers except the GS register, which have a limit here. So what that means is, for our code segment, for instance, will have a limit register here. So we can't go outside of this boundary, which is basically the guest kernel memory. Or the stack segment, again, can't go outside here. The data segment register can't go outside here. But if you use the G segment, the G segment limit is here. And so the G segment can have access to everything. So what then we're going to do is we are going to make sure that we use the G segment for any time we want to get up into here, either for data. So this might be, for instance, emulated virtual state, like let's say virtual E flags. That will store up here where the guest kernel has no access to it, can't see it, doesn't know it exists. So what we're going to do then is this acts as a limit or a jail in which the kernel runs, so it can't have access to all this VMM code and virtual state, as long as the kernel code doesn't use GS. So what we're going to make sure that we do is, when we do binary translation, if we have something that has from code that uses GS, we're going to put that and turn that into to code that doesn't use GS. So that's, again, now we're going to say any use of the GS register is privileged, just like use of the CR3 register is privileged, and the global descriptor table is privileged, and so on. But since we're in charge of the translation, we're in charge of the code that executes on behalf of this guest kernel, we can ensure that it doesn't use the GS register. And then what we can do is, for instance, if we have a CLI in our from, go ahead and convert that into, I'm just going to ignore whatever's before and after the CLI. We can convert that into something like set the 0-bit in the GS segment at the appropriate offset. So we can be clearing now a bit in the virtual state up in the VMM protected area because the generated code we use is going to be using GS. So just keep in mind now for the GS register, here's the rule. The rule is that is only usable by the virtual machine monitor. When we translate code, we're going to translate code that if the translated code needs access to the VMM state, that is, the VMM decides, I want to emit some code that either calls a function in here or sets some data in here, it's going to be using the GS register, sorry, the GS segment to do that. And so that allows us access there. Now we make sure the kernel can't have access itself. We're going to, by doing that, we will go ahead and say that if any code that we're going to translate has a GS register, we're going to rewrite it so it doesn't use the GS register. And that way, we maintain our isolation. By sharing the same address space, that means we can have very cheap access to shared state. Again, as I pointed out, the CLI can turn into just a reference using the GS register up into the shared state. And so that can turn into just a single instruction, right? CLI can turn to that. So it actually can be faster to clear interrupts in our guest OS than it is to clear interrupts in the actual OS. And also, this translated code is safe. We can't violate the isolation after we've done the translation, because the translation is ensuring that after translation, the only use of the GS register is by VMM code that wants to access anything up in that upper half. What I'm going to look at now is how the binary translation actually translates chunk by chunk. How does this actually work? Okay, the translation of a particular chunk I'm not too interested in right now. So of a particular chunk, many of them are going to be identical, some are not. What I want to look at is how does the control flow work? How is it we're doing this dynamic binary translation? So the translation from one block to another block, I'm going to assume we can deal with that. So we can deal with checking to make sure there's GS register, any other privileged instructions, and compile those into something appropriate. So I'm going to look at a simple function. And we just go through, check whether something is prime or not. This is not a particularly fast algorithm, but it is straightforward. All right, so that is the code for this. Now, let's look at some actual assembly for this. Okay, so first we'll move, let's say, ECX into EDI. One thing, so we're going to look at some disassembly of this. One thing to note is it's not using GCC calling conventions, and also this is using the Intel syntax rather than AT&T syntax. So this is the destination. So we're moving EDI into ECX, so this is A. We're going to move 2 into ESI. We then compare ESI to ECX. So that's this comparison here, whether I is less than A. The move 2 into ESI is the I equals 2. And then we will all right, so if we look at this code, basically this tells us A is an ECX. We initialize I to 2. We go ahead and compare I to A. If I is greater than or equal to A, we're going to jump to prime, which goes ahead and moves 1 into EAX, which is the return result in return. Otherwise, then we're continuing through our loop here, where we are going to, so let's see, we are here. We move ECX into EAX, so that is A, and then this is a sign extension, let's even just ignore this. And then we divide by ESI. So ESI again is I. And then if we jump if that's 0, so that is if it's equal 0, we're going to jump to not prime. So not prime moves 0 into the return result may return. Otherwise, we need to then continue the loop. So we're going to go ahead and increment ESI, compare ESI to ECX. This is the test here, if I is less than A. And if it is less, then I'm going to jump back to next I. Otherwise, we're going to drop through, and we drop through into the prime, which is here. So the instructions go like this, and then these four like this. So what's going to happen is, again, all these are going to turn into identical, basically. But the thing to keep in mind is we can't just leave the addresses where they are, because of the fact that as we are translating basic blocks, some may get bigger. Because of the translation, they may get bigger, which means all of our labels are no good. So let's look at what will happen. Let's identify, let's say we are called upon to start translating. So we know we're going to be executing this code at is prime. There's been some, let's say, call to is prime or something else. We know we're going to do it. Our binary translation job is to go ahead and translate. So we are going to start looking at these instructions, and we are going to be looking for a couple of things. We are going to be looking for, is this privileged or not? Is any of this privileged? So we look and we say, okay, this is an instruction, not privileged, not privileged, not privileged, not privileged. But we have control change here, jump greater than or equal to prime. So that's where we're going to stop our basic block. So our first basic block we can identify is here. That's our first basic block. So how are we going to translate that? Well, mostly what we're going to do is translate it unchanged, because we don't have any, again, privileged instructions here. So this is going to become move ECX, EAX, move ESI2, compare ESI to ECX. And then this is where it's going to be somewhat different. Now we're going to actually replace this with two instructions. So we're going to have, just as we did before, a jump greater than or equal to. So we're going to do a jump greater than or equal to. Okay, so what we're doing is we're actually changing this code to say jump greater than or equal to. We can't jump directly to prime, because prime is a location that we have not yet translated. So we need to be able to translate it. So what we're going to do is take an ADDR is going to be some code that basically says do binary translation starting from prime. Okay. Once we've done the binary translation starting from prime, we'll replace this with the actual binary translation of prime. And similarly, the fall-through address will be a block that says do binary translation starting from the next instruction after this that we were following through from. In our case, we're just giving it a label, calling it next I, right? Note, of course, none of these labels actually exist. All these are just jump greater than to particular memory addresses. We're putting in the labels to be understandable. And then, once we've done the translation, what do? We start executing it. So we go ahead and move ECX into EAX, we move ESI into 2, we compare ESI to ECX, and then, depending on what the value of A is, we're going to either jump to prime or we're going to fall through to not prime. Let's say A was 3, then in that case, we are going to jump to the fall-through address. That is going to cause us now to make a call. So do binary translation starting from next I. How does that work? It's really some sort of a call into using the GS register translate, let's say, from next I. It's important that this doesn't mess with any of the registers, right? Because all of our registers are sacrosanct, let's say. So when we call into the translate of next I, it can then go ahead and save any registers it needs to do the translation, and it can translate back into here. So what will happen now, this code is going to go ahead and get replaced with the translation of the next block, starting at next I. Where is this block? Well, this block is move is not a control flow, CDG not control flow, IDIV not control flow, JZ control flow. So now we can go ahead and translate this. Put this translation in here. So this will be, move EAX, ECX, CDG, IDIV, ESI, jump 0, not prime. So this would be jump 0, and I'm going to put the actual, so jump 0 to here, and then otherwise jump to some new one here. All right. We also maintain a mapping. So the VMM stores a mapping from every address, like let's say is prime maps to here. And the next I, and when I say is prime, I mean this actual address. Next I maps to here. And so for every original address, which is the target of a control flow, we have a mapping. Let's actually write it this way, which is perhaps better. So we have original instruction address, and then we have the translated instruction address. We don't do that for every address. We only do that for the beginning of every basic block. Why do we need to do that? Well, if we look down here, let's say we increment ESI, we compare this, and we jump less than to next I. So if we look at the translation of this, it's going to, again, be an increment, be a compare, and we can replace this jump less than next I, not with a new block that needs to be translated, but instead we say, hey, we've already translated this block. How do we know we translated this block? Because we look up next I. Next I actually is in here. That original instruction address was here. We look and we say, we have translated this block. What is the address of this block? The address of this block is next I right here. So when we do the translation, this is going to be a jump long directly to this block. So it is important as we are translating that if we execute a basic block, or we are going to jump to a basic block that we've already seen, that we go to the already translated version of that basic block. So the key thing that we don't want to do is retranslate basic blocks. We want to make sure that any basic blocks that have been translated, that we then can go ahead and execute those at full speed. There are optimizations that can be done. So for instance, we can go ahead, right, this is the translation of is prime. If we could arrange it such that we moved this or had this code right here directly, so that the fall through translated code was after the translated code of the thing that fell before it. So basically we make sure that if this could fall through to here, that when we translated, the translated code here falls in the translated code here, then we don't need this extra jump here. So things that are not identical translations. So one is going to be any privileged instructions, of course, and that we'll need to go ahead and translate. It may be calls into the VMM. It may just be manipulations of data in the VMM. Again, for like the clear interrupts or set interrupts. So PC relevant addressing. So we will turn something that says jump 10 instructions ahead into jumping into some sort of a label here of a basic block that needs translating. Any direct control flow, like jumps or calls, we have to change because the addresses, again, are changing. So the binding of the address happens at translation time. So for instance, when we translate this into this, we are going ahead and translating the jump greater than prime, which was a fixed location, so direct location, to a fixed location here of taken address or fall through address. If we have an indirect control flow, that's a little more complicated. Let's say we do a indirect jump. In that case, we need to go look at the register containing the address and then go through this table to figure out. So there's actually a hash table that contains the mapping from the original instruction address to the translated instruction address. So we will emit code that goes ahead and looks at the value of the register, looks up in our hash table what the correct translated instruction to is, and goes to there. So we're going to be emitting some runtime code. Things to note about the dynamic binary translation. One thing to note is that we pay some price of translation as we start executing previously unexecuted code. So for instance, the is prime, we would go ahead and translate the is prime, then translate the next I, then translate the next basic block. Once we translated those 3 basic blocks, then all of a sudden, we're going to be running at full speed, calculating whether this is a prime or not, running through our for loop, running through our for loop, running through our for loop, until eventually we're going to either execute the prime or the not prime basic block, and then exit. So what you'll find is the first call to is prime, we are going to have one basic block that is actually untranslated, either the prime or the is prime, depending on what our parameter was. That means that, again, we are doing demand-driven translation. So there are many code paths that never get executed, lots of error code handling and things like that, and that just never gets translated, or only gets translated on demand. So that reduces the cost of doing this translation because of the fact that we're doing it on demand. Also, just keep in mind, I mean, it's a fairly complicated, intricate process that we have to do. But that is how also just-in-time translation works for, let's give an example. So the MacBooks are going to be coming out using ARM processors, but they're actually going to be able to still execute x86 instructions in what way? Using a binary translation. So the difference is that instead of translating 1 for 1, and then let the CPU run full speed, we're going to translate from x86 into ARM code. Probably exactly that same idea of basic blocks, though. The difference is just from basic blocks will be x86 code, the 2 basic blocks will be ARM code.